Hello, grade 10s, and welcome back to chemical bonding. Now, in the last lesson, we focused on covalent bonds. We defined covalent bonds and we looked at how to draw Lewis dot diagrams for covalent bonds. And in this lesson, we are going to consider ionic bonds. What is an ionic bond? An ionic bond involves the transfer of electrons between a metal and a nonmetal. So if we take a look at this picture here, we have an atom that transfers an electron, could be more than one electron, but in this case it's one electron, to another atom. So one atom has an extra electron or extra electrons in its outermost energy level, which it would like to get rid of in order to have full outer energy level. And then we have another atom that wants an electron, or sometimes more than one electron, in order to have a full outer energy level. The atom that gives up an electron becomes positively charged. That will always be the metal. The atom that gains an electron will become negatively charged, and that will always be the nonmetal. Remember that an ion is an element that has lost or gained an electron or more than one electron. So an ion is an element that either has a positive charge or a negative charge. Ionic bonds occur when elements transfer electrons, and they do that in order to have a full outer energy level. The overall ionic compound is always neutral. So once a metal and a nonmetal have bonded in an ionic bond, they form a compound that is neutral. So let's look at this example. Lithium has one valence electron. Now, we know that because we know that lithium exists in the first column of the periodic table. And as we work through these sections, we always have to have a periodic table in front of us that's labeled with all the relevant information. Now, lithium wants to give up that valence electron because by giving up that valence electron, then its outermost energy level will be full. So by getting rid of this valence electron, it will only expose its core electrons. Fluorine, on the other hand, has 7 valence electrons. Now, fluorine would need to gain a valence electron in order to have a full outer energy level. So fluorine has got 7 valence electrons, and an 8th one will ensure that it has a full outer energy level. So lithium will transfer its valence electron to fluorine. Lithium now becomes a lithium ion, and the lithium ion is Li+. And again, we know that just by looking at the periodic table. We know that because lithium is in the first column of the periodic table, it has one valence electron, and it has a valency of 1+. So lithium forms a cation, and your metals will always form positive ions, which are also known as cations. Fluorine gains an electron. Now again, by looking at the column where fluorine exists, which is column 17 of the periodic table, we can identify that the fluoride ion becomes F-. And we also know from the column that it's in that fluorine, the atom, has 7 valence electrons. So this fluoride ion, specifically an anion, because it is negatively charged, is F1-, or simply minus. Now, the fact that one atom is positively charged and the other atom is negatively charged, well, that creates an electrostatic force of attraction between them. And that is what results in the compound lithium fluoride. So here we can see the lithium atom gives away its electron to the fluorine atom, once fluorine turns into an ion, remember it is called fluoride. And this results in the formation of the compound lithium fluoride. Now we need to learn how to draw Lewis dot diagrams for ionic bonds. But it's not as straightforward as covalent bonds because we need to be able to show the two half reactions, the full reaction, and the final product. Let's take a look at the first half reaction. The first half reaction will always involve the metal. We start off with a lithium atom. Lithium has one valence electron. Now, lithium gives away this valence electron and becomes lithium plus. So on the reactant side, we've just got our metal atom. We have to indicate the number of valence electrons. And on the product side, we are going to have the metal ion plus the number of electrons that it gave up in order to have a full outer energy level. So we know that because lithium forms Li+, it gives away one electron. So the first half reaction always applies to the metal. Let's look at the second half reaction. In this case, we've got fluorine. Fluorine has got 7 valence electrons, and we can figure that out by looking at the column in which fluorine exists on the periodic table. Now, in this case, the electron goes on the reactant side. So there is never a situation where we have electrons on the reactant side for both half reactions or the electrons on the product side for both half reactions. For the metal, the electron always goes on the product side, and for the non-metal, the electron always goes on the reactant side. So fluorine has got 7 valence electrons, and it needs to gain one more electron in order to have a full outer energy level. So here we've got fluorine with its 7 electrons. Fluorine now becomes negatively charged because it has gained an electron from lithium. So if we want to try and track this, what we can see is that this X here represents lithium valence electron, which it then releases. It then gives that valence electron to fluorine. So this X is the same as this electron, which is the same as this electron, which is the same as this X over here, to form fluorine with an extra electron, giving it a negative charge, so now it becomes the fluoride ion. Now, the next step for the full reaction is really very, very simple. All we need to do is copy out everything on the left-hand side of the equation and anything on the right-hand side of the equation, always starting with the metal, followed by the non-metal. For the full reaction, you may or may not indicate the number of electrons. It doesn't matter. You'll see later that we just use these electrons to help us balance these equations. So I just ignore the electrons. So I've got one electron being given away here, one electron gained here. That means that my equation is balanced. You'll see what I mean a little bit later. And so I'm just going to ignore my electrons in my full reaction. So my full reaction shows the original lithium atom with its 1 valence electron, the original fluorine atom with its 7 valence electrons, and that makes lithium plus. Remember, it lost its valence electron in order to have a full outer energy level. And this fluoride ion has gained that valence electron from fluorine, so now it becomes negatively charged. Now, in terms of the final product, it might look a little bit strange, but that is the Lewis notation. It is simply how we have to represent it using Lewis notation. So we are going to show our positive ion, and then in a square bracket, we show our negative ion. We have to show all the valence electrons around the negative ion. Now remember that the negative ion is going to be fully surrounded with 8 valence electrons. The positive ion is going to have no valence electrons around it, always. We have to indicate the plus here. We have to indicate the minus outside of the square bracket. Now we're going to practice a few more of these, but before we do, I'm just going to mention all ionic compounds exist as solids. Later on, where we have to represent chemical reactions and we have to show the state of each substance, whether it's a solid or a liquid or a gas, keeping in mind that all ionic compounds are solids is really, really going to help. What happens in the case of ionic compounds is that the positive and negative ions attract one another so that they form a three-dimensional network structure, also known as a crystal lattice. Here is a microscopic representation of lithium fluoride. So here we have a lithium fluoride compound. Now remember that positive charges and negative charges attract each other, but positive charges repel and negative charges repel. So that means that the next compound of lithium fluoride will orientate itself in such a way that repulsion is minimized and attraction is maximized. So if this is one compound of lithium fluoride, and this is another one, and this is another one, we can see that they orientate themselves in such a way that the positive lithium of the next compound is attracted to the negative fluoride of the previous compound. And the negative fluoride of the next compound is attracted to the positive lithium of the previous compound. And so this is exactly what creates that crystal lattice structure. This is why anything that is ionically bonded forms a solid crystalline formation. And we can see this kind of formation based on lithium fluoride in these diagrams over here. The reason that they do this is in order to maximize attraction and to minimize repulsion. Let's take a look at more examples of Lewis dot diagrams indicating half reactions, full reaction, and final product. We're going to do it for NaCl, sodium chloride, also known as table salt, AlN, which is aluminium nitride, K2S, which is potassium sulfide, and Al2O3, which is aluminium oxide. Let's start off with sodium chloride. The first half reaction shows us that sodium has one valence electron. That sodium atom wants to give up that valence electron, so it becomes Na plus an electron on the product side. The second half reaction will deal with a nonmetal. So here we've got a chlorine atom. A chlorine atom has 7 valence electrons. It needs one more electron in order to have a full outer energy level, and then it becomes the chloride ion, which is Cl-. Now remember that these electrons are there for balancing. We have one electron being given away here and one electron being gained here, so we're happy and we can just ignore the electrons in our full reaction. Our full reaction always starts with a positive ion, and all we need to do is copy across half reaction 1 and half reaction 2. So I'm copying the Na with its 1 valence electron plus Cl with its 7 valence electrons, and that forms Na plus and Cl minus. The Na plus does not have any valence electrons around it. It has given up its valence electron in order to have a full outer energy level. And the Cl minus now has 8 valence electrons around it. It has a full outer energy level. And the final product has to be represented like this. The positive ion outside of the square bracket, the negative ion with all its valence electrons. By definition, it will have all 8 valence electrons around it, with a charge of the negative ion outside the square bracket. Let's do this for aluminium nitride. The first half reaction, well, we've got aluminium. Aluminium has 3 valence electrons. Aluminium wants to give away those 3 electrons, and it forms the ion aluminium 3+. The nitrogen atom has got 5 valence electrons. Therefore, it wants to gain 3 electrons to become 3-. So here we can see on the product side a nitrogen atom with all 8 valence electrons surrounding it. 3 of them come from aluminium because it needs to gain 3. Now we need to make sure that our electrons are balanced, and they are, because I've got 3 on the product side here and 3 on the reactant side. So I'm happy, and I can now move on to the full reaction. Again, for the full reaction, all I need to do is copy this across, plus this, and that makes this, plus this. So again, the full reaction is just a copying exercise. You copy out everything on the left-hand side and everything on the right-hand side of the equation. You put the 2 half reactions together, always starting with the metal. So aluminium has 3 valence electrons, nitrogen has 5 valence electrons. Aluminium gives away those 3 valence electrons to become Al3+. It now doesn't have any dots or crosses around it. And nitrogen gains 3 valence electrons in order to become the nitride ion, which is N3-, and it has all 8 valence electrons surrounding it. And finally, the final product, we show the positive ion outside the square bracket, the negative ion inside the square bracket with all the electrons surrounding it, with a 3- or the charge of the negative ion outside of the square bracket. Let's take a look at potassium sulfide, K2S. Now this one will involve balancing of electrons before we can get to our final reaction. So the first half reaction shows us potassium that has 1 valence electron. That makes potassium with a positive charge because it has given away an electron. The second half reaction shows us a sulfur atom. Now, sulfur has got 6 valence electrons. It therefore needs 2 electrons in order to make S2-. Remember, based on sulfur's position on the periodic table, we know that sulfur has 6 valence electrons and that the valency of sulfur is 2-, and that's all it can ever be. But what we can see now is that potassium can only give up 1 electron. That's all a potassium atom can ever give up. And sulfur needs 2 electrons. And this kind of indicates to us why the final compound is K2S. But we don't need to think about that too much. What we need to do is make sure that we balance our electrons. So in this case, the number of electrons is not balanced. Potassium can give away 1 electron, but sulfur needs 2 electrons. So we need to balance out the number of electrons to get to the ratio in which the elements in this compound exist. we need to find the lowest common denominator, which in this case is obviously 2. So we're going to double up everything in this half reaction. So by balancing out the first half reaction, by multiplying it by 2, we are going to create a situation where we've got 2 electrons here. And once we have 2 electrons here and 2 electrons here, then we have 2 half reactions that are balanced, and we can move on to the final reaction. So my first half reaction that is balanced is going to look like this. 2K makes 2K plus 2 electrons. My half reaction for sulfur remains exactly the same. What we were trying to get at is we were trying to get the same number of electrons on the product side of the first half reaction as the reactant side of the second half reaction. And now we may move on to the full reaction. Again, simply copying, starting with a metal, followed by the non-metal, and we can ignore the electrons. Remember, we use those electrons as a crutch to balance our equation. So we've got 2K plus S makes 2K plus S2 minus. We're just copying the reactants and the products. And finally, to show the final product, we need to show the fact that there's 2 potassium atoms on the left. That is just Lewis notation. So we don't show it as a subscript, we show it on the left. Again, that is what Lewis notation requires, whether or not it makes sense. We are going to show the metal without any valence electrons surrounding it. The non-metal is going to be fully surrounded by valence electrons, and the charge of the non-metal falls outside the square bracket. Finally, let's do aluminium oxide, Al2O3. This is another example that's going to involve balancing, and we can already see that up front because we've got subscript numbers here. And in this case, we're actually going to have to balance both of them to reach a lowest common denominator. So let's take a look. We have got aluminium that has 3 valence electrons. Aluminium wants to give up 3 electrons to have a full outer energy level to form Al3+. Then we've got oxygen. Now, an oxygen atom has got 6 valence electrons, and an oxygen atom wants to gain 2 electrons in order to have a full outer energy level. So in this case, again, the number of electrons is not balanced. Aluminium wants to give away 3 electrons. It has to give away 3 electrons. It can't choose to give away 1 or 2 or 3. It wants to have a full outer energy level. Therefore, it has to lose 3 electrons. Oxygen may only gain 2 electrons to have a full outer energy level. It can't just choose to gain 1 electron because then it is still not happy. Right, so now what we need to do is we need to somehow balance these electrons. We need to find a lowest common number between 3 and 2. And that number is going to be 6. So if I multiply the first half reaction by 2, then I will reach 6 electrons. And if I multiply the second half reaction by 3, then I will reach 6 electrons. And once my electrons are balanced, then I'm happy. So let's take a look. My first half reaction balanced needs to be multiplied by 2 all the way across. So I have 2 aluminium atoms that will form 2 aluminium 3 pluses, and because I have 2 aluminium atoms and each one gives away 3 electrons, the total of electrons that's being given away by aluminium is 6 electrons. The second reaction needs to be multiplied by 3 all the way across in order to reach that same number of electrons, which is 6 electrons. So that means that 3 oxygen atoms in total will need 6 electrons to form 3 oxide ions. Now that our electrons have been balanced, we're happy, and we may move forward to the full reaction. Remember that the full reaction, you're just copying across what you see on the left-hand side of the arrow and what you see on the right-hand side of the arrow, always starting with a metal. So 2 aluminiums with 3 valence electrons around them and 3 oxygen atoms with 6 valence electrons around them will make 2 Al3 pluses plus 3 O2 minuses. Remember that because aluminium's given up its valence electrons to have a full outer energy level, we do not represent any valence electrons around aluminium once it's an ion, and oxygen, once it is the oxide ion, is going to have a full 8 valence electrons surrounding it. And finally, for the final product, remember that in Lewis notation, we don't show the 2 and the 3 as subscripts, we show it to the left of each element. So I've got 2 Al3 pluses, I put the 3 and the charge outside the square bracket, and inside the square bracket I show my nonmetal with all 8 valence electrons surrounding it. I'm going to end off this lesson by reminding you that should on an exam they ask you to provide the Lewis notation for anything that is ionically bonded, don't try to create a Lewis dot diagram like we did for covalent bonds. Look very carefully to see if they're asking you for the Lewis notation of something that's covalently bonded, in which case you have to show sharing of electrons like we did in the last lesson. But sometimes they ask you for the Lewis notation of something that is ionically bonded. But they don't ask you to show the half reaction and the full reaction. They just want the final product. They just want the compound. You have to remember to show it like this.